for today's notes, what we are going to start doing is we are going to start actually graphing our trig functions on your coordinate plane. Instead of using the unit circle, we're going to be graphing them. So today we're going to be dealing with our parent trig graphs, which if you remember, your parent graphs are just the most basic form. It doesn't get any simpler than these ones. So we're going to go through these ones. What you want to do is you want to memorize what the shape of these look like. And then we'll be able to do our transformations with it in a couple of days. So one way you could do these is by creating a table of values. So when you're doing your table of values for these, you're only going to deal with your quadrantals that we were dealing with in our unit circle. So you got your 0, which is still right here at the origin. You want to deal with 90, but we always put it in radian form. So we're going to use pi over 2. And then 180, 270, and 360. So that's what each of these little tick marks represents. There's your 90, there's your 180, there's your 270, and there's your 360. So pi over 2 pi, 3 pi over 2, and 2 pi. The other thing you want to do is you want to kind of label them, your y-axes. We'll just do, each tick mark is a quarter, so up 4 will give us 1. This just spreads out our graph so that you can actually see the picture of it, see the shape of it a little bit better. We want to try to spread it out. So, if we have sine in here, we plug it in, try to find our sine value. Sine value of 0 is 0. You could use your unit circle also for that. Sine value of 90 is 1, 180 is 0, 270 is negative 1, 360 is 0 again. So let's plot those. Try to line it up as best you can. And then again, these are curves, so you want to make sure you draw curves. So that's our f of x equals sine x. That's our sine curve right there. Sine curves always start at 0 and they end at 0. That's kind of your hint of one period, as we call it. So our domain here would be XER. Yes, we only use 0, 90, 180, 270, and 360 to make the graph, but really it's every value in between there also, which is why it's a curve and not just specific points. Our range is going from negative 1 to positive 1. Negative 1 is our lowest, positive 1 is our highest. Just like in our unit circle. Positive, or the highest value you could get was 1. You can't have anything over 1. And then our graph starts at 0, 0. So really what we've done here is we've taken our unit circle and we've kind of cut it in half. So 0 to 90, that represents all of our first quadrant angles. And then there's your 90. So 90 to 180, that represents your second quadrant angles. 180 to 270, there's your quadrant 3. 270 to 360, there's your quadrant 4. So you kind of want to picture, if I took this and I moved it over this way, it kind of creates your circle almost. So what we've done is we've just cut it and we've made it a sine curve instead of a unit circle. So it's all the same values, we're just representing it in a different way. So let's take a look at our cosine. We're going to do the same thing for our cosine. Let's start with a table. We're going to use the same values, 0, 90, 180, 270, and 360. 0, 90, 180, 270, and 360. And again, we'll do 1 and negative 1. So our cosine at 0 is 1, 0, negative 1, 0, 1. So this time our cosine curve starts up here, goes down to 0, down to negative 1, up to 370, back up to 1. So again, you want to make it a curve. There we go. That's our cosine curve. Again, our domain, much like our sine curve, is going to be x as an element of the reals. It can be every single x value. Our range is the same again, -1 to 1. But this time, it starts at the point 0, 1. It doesn't start at 0, 0. It starts up at 1. And same thing still holds true. Here's your quadrant 1 between 0 and 90. Here's our quadrant 2 between 90 and 180. Quadrant 3. Actually, I should put it up here since the values are up here. There's our quadrant 4. So if you remember, in our unit circle, cosine's positive in 1 and 4. Sine is positive in 1 and 2. So it's all the same rules, just written in a different way. And then let's take a look at our other one on the back, our tangent one. Tangent is a little trickier to draw. Again, we can still make a table. We are still going to use the same values, so you are going to know and love these values while we do our trig graphing. Zero, 90, 180, 270, and 360. This time we're not going to spread it out as much. So there's 1, -1. So for our tangent values, 0 is 0, 90 is undefined, 180 is 0, 270 is undefined, and 360 is 0. So what happens is at 90 and 270, since those are undefined, you have to draw your asymptote line. They're vertical asymptotes since they're undefined. So you got to draw in your little dotted lines there for those. And then the only other values we know are 0, 0, and 0. So it doesn't really help us too much when it comes to drawing our trig graph. So I'll help you out with the rest of it. That curves up like that along your asymptote at 180. You got a piece like that, so over to the left of 180, it's down, to the right is up. And then 360 is going down. So this one's a lot different than those other two. So our domain this time is x cannot equal 90 or 270. So it'd be everything else, just not 90, not 270. Our range this time is y is an element of the real. It can be anything. Because of those arrows going up and down, it can be any number. And then our vertical asymptotes are at pi over 2 and 3 pi over 2. Now the one thing about these graphs that I haven't done yet is they do continue on. We're only looking for right now from between 0 and 360. So your 0 to your 2 pi. They do continue on and the patterns repeat themselves. So like for this tangent one, if I were to continue beyond 360, my graph would keep going up there. And I'd have another vertical asymptote here. And then I'd have another one of these shapes over here, and then a vertical asymptote, and then another one and a vertical asymptote. So that shape keeps repeating. So in this graph, our asymptotes are at pi over 2 and 3 pi over 2. If it kept going, it's always an odd number in front of your pi. So 1 pi over 2, 3 pi over 2. There'd be another one at 5 pi over 2 and 7 pi over 2. The other thing I didn't do just yet is you can graph these in your calculator. So I'm going to pull up my calculator. Let's have you grab yours. So let's graph the sine one first. So we'll go to our y equals. I got something down here in my y4, so I'm going to clear that out first. And go back up to my y1. So I'm going to type in that I want to graph just the sine of x. Now don't push your graph yet because it's not going to work. You're going to see some funky stuff. We got to go to zoom, and then you want the one that says trig. That's what changes your axes to be 0, 90, 180, 270, 360. So as I was saying, we graphed before from here to here. We graph just this part of the sine curve. As you can see, it just continues on and it keeps repeating itself even in the negative values there. So that just keeps going on forever and it's always going to keep following this little loop here. Let's look at our cosine one. Cosine x. We already are in zoom trig, so I don't need to fix that. So again, see, cosine starts at 1. We looked at this part of the graph before. It continues going on in the other direction. So that curve just keeps going and going and going and going. And then our last one, tangent of x. The calculator can't show you the asymptotes. But you would have an asymptote here, you'd have an asymptote here, you'd have one here, you'd have one here, and it just keeps repeating that same shape over and over and over again. Okay, so as I was saying, those are our parent graphs. Those are the basic shapes of them. What we need to do sometimes is we are going to move them around the graph. So we have various letters here. We got A out in front. B is right there. We got our C. And we got our D value. No matter which one you're looking at, sine or cosine, those letters are all going to mean the same thing. So our A deals with our amplitude. That's how high the graph is going. So this is going to be the height of the graph. It also can tell you if it's switching direction. So like normally they start at certain directions, but sometimes they can get reflected over the x-axis. That would happen with your A value. B affects the period, which we're not going to get too much into today. We're going to do that in a couple days. C is your phase shift, which means moving it left-right, which is just like normal functions. When you're next to x, you move left-right. And then D is your vertical shift. That's your up-down. Just like all your other functions at the end, that's your up-down. So here we have graphed cosine of x from negative 2 pi to positive 2 pi. So that's negative 360 to positive 360. They want us to graph a couple of other ones. So they want us to graph j of x equals 3 times the cosine of x. So what's different with this graph from the first one is your amplitude is a 3. So what that means is, instead of this being at 1, you're going to do it times a 3. So that point's going to be up here at 3. 0 times 3 is still 0. Negative 1 times 3 is negative 3. 0, and then 3. And then that repeats itself over here on the left side as well. And then you can go and create your curve. So I'm just going to label this as my j of x curve. So my amplitude changed to a 3. It makes my graph taller. Instead of my range being from 1 to negative 1 to 1, like my original one was, my range now is negative 3 to 3 because my amplitude got changed to a 3. Now they want us to graph this one, 1/2 cosine of x. So instead of things getting bigger, it's going to end up getting smaller. So this 1 times 1/2 would give me 1/2. That would still be 0. This would be negative 1/2, 0, positive 1/2. And again, it just repeats itself over on the other side. So this creates just this little tiny curve, j of x. So our range for this one would be negative 1/2 to positive 1/2 because your amplitude is a 1/2. So that's what that changes. It changes the height of your graph. So if we look at the next part, amplitude answers the question of how high or low does the graph go around the midline. Whenever they ask you what the amplitude is, it's always positive. And I'll show you what I mean in a minute. So if you're looking at an equation, your amplitude is the number in front. If you're looking at the graph, It's the height of your bump. So your amplitude affects the range of your function. Oh, when I talk about height of your bump, let me go back to that for 1 second. So let's say there's my sine curve. That part right there, that's the height of your bump. That's your amplitude. Okay. So here they want us to find the amplitude and the range. So for this one, our amplitude would be 3. So that means our range would go from -3 to +3. You would just take your parent function, multiply that range times 3, -3 to +3. For number 2, right now I'm going to take this off. Don't need that right now. So our amplitude here, a lot of people would tell me -4, but no, our amplitude is always positive, as I said. So our amplitude there is a 4. Our range would be -4 to +4. So here given f of x equals 2 cosine of x and g of x equals -2 cosine of x, what is the transformation? So let's sketch this a little quickly. This one means it looks like that. When you put this negative here, instead of starting at +2, it's going to start at -2, and it makes your whole graph flip. So the transformation would be a reflection over the x-axis. Again, it's just like all of our other transformations we did with our functions throughout the year. You put a negative out in front, it makes it reflect over your x-axis. That doesn't change. So here, they want us to graph sine of x and -3 sine of x using the domain -2 pi to +2 pi. So I'm going to do my sine of x first. So my sine of x, that's just my normal parent function. If you have it memorized, you don't really need a table for it. Everything goes 1 to -1. So there's my f of x. So here, you can make yourself a table. Some people love tables. I could have made a table for this one down here that I just drew if you really wanted to. If it's -3 sine of x, you just take your sine values and multiply them times -3. So that would be 0. That would be -3, 0, +3, and 0. So 0, 1, 2, 3, 0, 1, 2, 3, 0. And again, it would repeat. This one was -1, so it's going to become +3, because -1 times -3 is +3. That one was a little messy. But there it is. So it flips direction with that negative sign in there. So our amplitude was 3, and it reflected over